Assalamualaikum and good morning everyone. Today, we're going to present our project that is determination of sodium in white bread using wet digestion method and atomic absorption spectroscopy. My name is Hanis Masara and I am presenting with my group members Fakrul Nabil Iman and Hasmin Danis Nuriman Norris. Introduction. Sodium is an essential electrolyte required for nerve impulse, transmission, muscle contraction and maintaining fluid balance in the human body. However, excessive sodium intake is associated with health problems such as hypertension, stroke and kidney disease. White bread is widely consumed, especially during breakfast, and is a significant contributor to daily sodium intake. The objective of the study is to determine the sodium content in white bread using wet digestion method followed by atomic absorption spectroscopy. The problem statement of this study is that nutritional labels may not always accurately reflect the actual sodium content of food products due to variations in formulation and processing. Therefore, the hypothesis of the study is that the sodium content determined experimentally using the wet digestion method followed by atomic absorption spectroscopy is different from the sodium value stated on the nutritional label.
Next, this slide presents the literature review related to the method used for sodium analysis, particularly wet digestion and atomic absorption spectroscopy. First, Ajart et al. 2016 investigated the use of wet digestion using nitric acid and hydrogen peroxide. Their study showed that this method achieved complete mineralization of samples. Wet digestion involved the use of acids to break down food samples, making the minerals available for analysis. This method is often compared with other digestion techniques such as dry ashing and microwave digestions. Wet digestion typically uses a mixture of nitric acid and hydrogen peroxide to achieve complete mineralization of the sample. Next, Julsham et al. 2005 focused on atomic absorption spectroscopy as an analytical technique. Their finding demonstrated that AAS provides high precision and accuracy for sodium quantification. Atomic absorption spectroscopy is a widely used technique for the quantification of sodium in food samples. It offers high precision and accuracy, making it suitable for regulatory and quality control purposes. The method involves atomizing the sample and measuring the absorption of light at a specific wavelength by sodium atoms. Then, Noel et al. 2008 compared wet digestion with other preparation method, which is microwave digestion. This method is faster and often yield higher recovery rates compared to wet digestion. For instance, in the analysis of dairy products, microwave digestion showed a recovery rate of 96.88% compared to 87.18% for dairy aging. However, wet digestion remains a reliable method with consistent result. While dry aging is less labor-intensive, it may not be as effective in completely breaking down the sample, potentially lead to lower sodium recovery rates. Next, Schoenfuss et al. 2014 compared dry aging and wet digestion method for sodium analysis. Their study found that dry aging may result in a lower sodium recovery rates, highlight a limitation of this method when compared to wet digestion. This study is important because it helps justify the selection of more reliable analytical methods in sodium determination. Next, Torina et al. 2019 focused on the analysis of sodium content across different types of bread. Their findings showed consistent sodium levels among various bread samples, supporting the reliability of routine sodium analysis methods. This study is particularly relevant as it validates the use of these methods for assessing sodium content in commonly consumed foods like bread. Lastly, Lee et al. 2010 examined sodium analysis in the context of public health monitoring. Their work was used to monitor sodium levels in school meals and other food items, emphasizing the importance of accurate sodium measurement for dietary guidelines and public health policies. Overall, these studies provide strong support for the chosen analytical approach and highlight the importance of accurate sodium determination in food analysis and public health.
Next, methodology. First, 4 brands of commercial white bread were purchased from local markets in Perlis. Each bread sample was homogenized and approximately 5.0 grams were accurately weighed. All reagents used were of analytical grade and deionized water was used to avoid contamination. Next, wet digestion was carried out to remove the organic matters of the bread and release sodium into solution. Each sample was treated with concentrated hydrochloric acid and heated until a clear solution was obtained, indicating complete digestion. The digested sample were then diluted to a known volume, and blank digestions were prepared for corrections. Sodium determination was performed using flame atomic adsorption spectroscopy at a wavelength of 589.00 nanometer. A series of sodium standard solutions was prepared to construct a calibration curve with excellent linearity. Finally, the absorbance readings were recorded in triplicate, and the sodium content of each bread sample was calculated and expressed in milligrams per kilogram after considering dilution factors.
Result and discussion. The instrumental condition used for sodium determination by flame atomic exertion spectroscopy (FAS) are summarized in Table 1. Sodium was analyzed at a wavelength of 589 nanometer using a slitwise of 0.7 km with a burning height of 7.4 mm and a fume flow rate of 2.5 liter per minute. This setting are typical for achieving stable atomization in optimal sensitivity for sodium in an air-acetylene flame. The lamp current, Banach alignment, and photomultiplier voltage were adjusted to maximize signal intensity while minimizing noise. Under this optimized condition, the instrument produced a linear calibration curve with an excellent correlation coefficient of R² equal to 0.9976, confirming strong proportionality between absorbent and sodium concentration. The calibration plot is shown in Figure 1, demonstrating that the method is suitable for quantitative analysis within the working range of the standards. The absorbent values and calculate sodium concentration for the bread sample are present in Table 2. The sodium content for the 4 commercial white bread sample range from 352 to 413 mg per kilogram. Massimo record the lowest sodium content, which is 352, followed by Mighty White 362 and Eco 372, while Gardenia exhibited the highest sodium concentration at 413 mg per kilogram. This variation likely reflects the difference in formulation, particularly the amount of add, salt, and leavening agent used by each manufacturer. Since sodium chloride contributes to dough structure, yeast activity, and flavor, manufacturing often adjusts salt level to achieve desired sensory and textural properties, resulting in inter-brand variability. To evaluate the accuracy of the analytical method, the obtained sodium concentration will compare with certified reference value as shown in Table 3. The percentage accuracy ranged from negative 19.6% to positive 1.6%. with Eco showing the closest agreement to its reference value, which is positive 1.6%. Mighty White also demonstrates acceptable accuracy at negative 5.9%. However, Massimo, negative 13.9%, and Gardenia, 19.6%, show higher deviation, which may be attributed to metric effect, incomplete digestion, or slight calibration drift during measurement. Bread matrices contain carbohydrate, fats, and additives that may not fully decompose during wet digestion, potentially affecting sodium recovery. Despite this deviation, the accuracy value remains within a reasonable range for routine food quality assessment. Overall, the combination of wet digestion and AAS proved effective for determining sodium in white bread sample. The method demonstrates strong calibration linearity, acceptable accuracy, and good sensitivity for sodium level typically found in processed food. The sodium concentration obtained in the study fall within the range commonly reported for commercial white bread in Malaysia and other countries, reinforcing the role of bread as a notable contributor to daily sodium intake. Continuous monitoring of sodium level in bread product is therefore important to support public health initiatives aimed at reducing dietary sodium consumption.
In conclusion, the sodium content in white bread has been successfully determined using wet digestion method followed by atomic absorption spectroscopy, where the concentration that we obtain is 369 for Mighty White, 353 for Massimo, 379 for Echo, and 414 for Gardenia. It has been proven that AAS can be accurately determine the sodium content in each bread samples, as well as the certified values on the labels of these breads. Therefore, the nutritional labels on these breads can be verified whether the stated sodium content in the labels is accurate or not.